Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 16 in our incredible new tutorial series where you're going to learn Fusion 360 or you're going to die trying. What I'm going to need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, I want to give a shout out to you guys who are helping me out over at Patreon. It is your support and your encouragement that keeps this great content coming. You guys that are not helping out yet, take a look down in the description. There is a link over to my Patreon account. Think about hopping on over there and hooking a brother up. But enough of this shameless self-promotion. Let's talk about what I am going to teach you today. And what I'm going to do is I'm going to teach you the proper use of vernier calipers, and I'm going to introduce you to the concept of design rules. Up until now in this class, we have just been designing things, just sort of winging it, kind of guessing on things like tolerances. But what I'm going to introduce you today to is the concept of having quantifiable design rules for your manufacturing capability. So you are designing for manufacturing in what technology? You need to understand the manufacturing limits of that technology. For this class, we're designing for a 3D printer, and specifically for the 3D printer that you are using, but more generally, whatever manufacturing technology you are designing to, you need to understand the manufacturing limits and the tolerances and the precision associated with that manufacturing technology, and you need to design to the design rules that are derived from the manufacturing capability that you will be using. For us, what is our manufacturing capability? It is the 3D printer. So when we design things, we need to understand the limits of the 3D printer that we're going to be using. Now again, we're going to spend several class periods on this topic, and I'm just going to introduce it today. But also today, what I'll be showing you is in order to understand and determine and define your design rules, you need to have good measurement equipment. And so what we will be using is these vernier calipers. Hopefully most of you guys have already ordered your vernier calipers. If you haven't, look down in the description. There is a link over to Amazon where you can pick up a great set of vernier calipers, and you'll be using the same ones that I am in this lesson. Okay, so that's probably enough introductory banter. Let's jump on over and let's get busy and actually start the lesson. I should show you that I've already designed my test structures, and I'm over here printing them as we're speaking because we're going to need these test structures in order to learn how to use the calipers. And so that is the little hum you hear in the background. That is the 3D printer running. But what I'll need you to do is hop on over here to Fusion 360, and we're going to design some very simple test structures that will allow us to get an initial look at the precision that we can get out of our 3D printer. And these will also be test structures that will allow us to begin to put together some design rules. Sound good? Okay, sounds good to me. So we will start. What we're going to do is we're just going to design a very simple cube. That cube is going to be 25 millimeters tall, 25 millimeters deep, and 25 millimeters wide. Then we're also going to design a little cylinder, and those are going to be our test structures. Now along the way, I want to continue to have you sharpen your Fusion 360 skills, and so I'll show you a couple of neat features. We'll learn a couple of neat new things about Fusion 360. So in this class, I want to be advancing our design skills, as in thinking like a good mechanical designer should. I want to continue to advance our Fusion 360 skills, and I want to continue to advance our printing skills. So I'm sort of rolling all of those together, and hopefully we'll be advancing all three of these in each new lesson that we come out with. Okay, let's see if we can design these structures. We'll start by creating a sketch. We will be sketching on the most excellent XY plane. Excuse me, that is the red-green plane, so I'll click there. I'll get this over here. I'll get this over here where you can see it better. Okay, and I'm going to start just by designing my cube. So I will select the square. I'll come over here. I am going to design a center point cube, which means we click on the center point that's right here. That will give you the center rectangle. And so we click on the origin, we click, and then I want this to be 25 wide. I'm going to tab and I want it to be 25 tall. Okay, boom, we have our cube. That looks good. Now what we're going to do is we are going to give ourselves a construction line. So I will select line. I will come over here, make it a construction type line, click on the origin, and I am going to come out about, I think I can come out about 60. So I'll make that 60 millimeters. We are working in millimeters. Now I'm going to design my cylinder. So I will get a circle. I will turn off construction line type. I will let this snap to the construction point here. And we are going to make this cylinder, we are going to make this cylinder a radius of 50. Okay, that will be the outside diameter. Now we're going to make another circle. We're going to hover over and let it snap to our construction point, and we will make this 30. Okay, yeah, we will make this 30. I'm trying to think. Yeah, 30 would be what I want to do. And then we have got our cylinder. We've got the sketch that will allow us to make our cylinder. So I'm going to go ahead and I'm going to finish the sketch. And then I will come to the home view and I will start extruding. We will start with our cube. I'm going to come up here and click on extrude, click on the rectangle, and we want to extrude a distance of 25. Okay, so this is 25 wide, 25 long, 25 tall. There is our test cube. Now let's turn our sketch back on. And then we're going to come to the inside. So the base of our cylinder is going to be 10 millimeters thick. So I will click extrude. I will make that 10. Okay, and then on the outside, the actual cylinder wall, we are going to make that 30. Okay. So we have made a test cylinder and we have made a test cube. Now, what you want to know is how precise can you manufacture this? We designed it to be exactly 25. How precisely can we manufacture it? Will it come out somewhere between 24 and 26? You know, like if we just print this, how precise is it? So we're going to want to measure all of these dimensions using our vernier calipers after we make them. But what I need you to see is I might have one precision along the y-axis and I might have a different precision along the x-axis. After I make this cube and this cylinder and take them off the build plate, I don't want to get confused about what the X manufacturing axis is and what the Y manufacturing axis is. So what we're going to do is we are going to label them. And in thus doing, we're going to learn a super cool tool that is in Fusion 360. So in order to label this, we are going to come up and we are going to create a new sketch. Now it's asking me where I want to create the sketch. I want to create it on the axis. I want to create it, on the face, and that I want to create it on the face here that is that is coming out the y-axis. So if we look, and let me make sure that you guys can see that. I'm going to turn the origin on over here, okay, and then you can see the X, Y, and Z axes, and you can see that this face is the face that is perpendicular to the green axis. It is the face that is perpendicular to the y-axis. And so what I'm going to want to do is I'm going to want to create a sketch on that plane. So here we are, we're ready to do our sketch, and what I'm going to do now is I'm going to add some text. Okay, I'm going to add some text, and I got to put a box where I want the text. So I'm going to hover over this corner. You can see it snaps to the corner. I'm going to click. I'm going to come down, let it hover over until it snaps to this corner. And there I've got a text box ready to put my text in. This face is perpendicular to which axis? The y-axis. So I'm going to label this y. I'm going to go ahead and make it bold, and then I want it centered left and right, and I want it centered up and down. So I select those two things, and boom, there it is. Now I want to also, because even though a cylinder is round, I want to label the face. I want to label the part of the curvature that is perpendicular to the y-axis. So I want to make another letter over here. I'll hover over the corner, click. I need to add text again. So I will go to text. I will hover over this corner. It's snapped. I click. I come down here and I let it snap and I click. And then this also is the y-axis coming out this direction. And everything else looks good, so boom. Now, if we went out and 3D printed this, we would get what? Absolutely nothing. So we need to finish the sketch. Now, one thing you see is that because I drew on this plane of this face, this Y is in the right position, but this Y is floating in mid-air in the middle of the cylinder. Never fear, because I'm going to introduce you to a new friend, and that new friend is most amazing. He hides under the Create menu, and it is Emboss. So let's start. We want to emboss this Y on this face. Now, the fact that this Y is already on the face, it doesn't matter. It doesn't have to be there. It just happens to be there in this case. So what do I want to emboss? I want to emboss the Y. Where do I want to emboss it? I want to emboss it on this face. And then what I want it to be is I want it to be a cut like that. I messed up. Okay, so I clear out of that. I am going to select this face. I want to select this profile. This Y is what I want to emboss. That is the profile. I select that. Now, where do I want to put it? On which face? I want to put it on this face. And then I want it to be a cut. And a depth of 2 is good, and I don't want to tweak with the position of it. So I will say OK. And boom, look at that. We have a Y. Why did I make it a cut? I could have had it stick out. The reason I didn't want it to stick out is, as I'm using my calipers, I don't want it to affect my measurement, and I couldn't measure the dimension of this in the center if that is sticking out. That's why I did a cut. I'm going to turn that sketch back on, and now I'm going to emboss this Y on the cylinder. Never fear that it's in the wrong place, because all you've got to do is you've got to come up here and you've got to say emboss. What is my sketch profile? It is this Y. And then what face do I want to emboss it on? I want to emboss it on the cylinder face. So I'm going to say select the face, and then I'm going to select the cylinder, and then I'm going to say OK. What did I do wrong? I didn't say cut. So I will come here I will come down to the timeline. Let me turn this off so you can see it. I will come down to the timeline. I'm going to right mouse click. I'm going to edit that last feature. I'm going to turn my title back on. And then I am going to be sure to come up here and say that is a cut. Okay, look at that. Now, if I just spin it around, I should see everything right. Although it seems like it undid, or for some reason this other one here is no longer cut. So let's see, that was that one. For some reason that seems to have not showing. Yeah, it's there. Let me turn the sketch. Oh, it's because it's behind it. I think maybe if I turn the sketch off. Yeah, if I turn the sketch off, it was the cut was hiding behind the sketch. And so that all looks good. So I've labeled the y-axis on both of these. Now let me talk to you a little bit about embossing, the magic of embossing on a curve. Now if you just straight out projected that text onto a curved surface, that would distort the text, especially if you had more text. It would distort it as it cut it. But emboss is very smart, and it conforms, it curves the emboss to a curved face, and therefore the text isn't distorted even if it was wrapping around the edges. And that's kind of the magic of the emboss tool. So I got a perfect Y. That Y is not distorted. Now let's go ahead and let's label the plane that is perpendicular to the x-axis. So I'm going to create another sketch. I'm going to have it on this face, and then I am going to create text. I want it to go from the corner of the rectangle down to the other corner, and then I want this one to say what? This one is the X. It is the X-axis, like that. Okay. Now I'm going to create another text. It is going to go from the corner of the cylinder down to the bottom corner. Let it snap, say OK, and we want that to be a Y, as we want that to be an X as well. All right. Now if I zoom in, this lower X is the one that I want on the cube. Now you can see that the Y one is offset because this X one here is offset. Why? Because it is going to be in the middle of the cylinder, and this one is going to be the middle of the cube, and the cube and the cylinder are different heights. That's why those two X's are offset. But I want to go ahead and finish my sketch. I'll go to the home view, and then what I'm going to do is, remember, the lower one goes to the cube face. So I'm going to come in and I'm going to create an emboss. That emboss is going to be this X. I want to emboss. I want to emboss it on this face. I want it to be a cut. I always forget that. I'm sorry. I want this to be what I'm going to emboss. And then I've got to come up and click select, and I want it put here, and then I want it to be a cut, and I want it to be a depth of -2. That's good. And boom, there it is. I will turn that sketch back on, and I will emboss again. I'm going to emboss this X, the higher one. I will choose select this time, and I'm going to emboss it on that face. I'm going to make it a cut, and I am going to say OK, and there it is. That's the X, that's the Y. I'll turn that sketch off, and that is looking really, really good. Now I also want to label this as the plane that is perpendicular to the Z-axis, so I will go top. I will create a sketch, and I'm going to go, I will create a sketch. Now I am going to add text. Oh, I'm still in the, okay, I'm in the sketch mode. And now I am going to create text from that corner down to this corner. This is the Z plane. All right, it's that all looks good. I will say okay. And then the cylinder, it's obvious what Z is, so I don't really need to label that. So I can finish my sketch. I can go to my home view. Wow, and it looks like I didn't do the sketch up here like I was expecting. I think that I hadn't clicked the face, and therefore when I did click it was down here, but never fear, that's going to work. I will say create an emboss. What is the profile I want to emboss? That Z. Come over here to select. Where do I want to put it? There. I want it to be a cut, and then I say okay, and there it is. Boom, look at that. So I have two test structures. Those two test structures are very precisely designed. The question is, how well can we manufacture them, and how do we make our measurements using our Vernier calipers? And so let's come over here and see how our print is going. It looks like it is doing pretty good. I've got the cylinder printing out. I've got the cube printing out. It looks like I've got most excellent adhesion on our Ender printer. I'll also show you my little wider shot there. Okay, here is the over-the-shoulder shot where you can see it being built. And what I'm going to do is, here in just a second, I'm going to pause. The video, and then what I'll do is I'll let these things finish printing, and then we will continue. We will continue with with the lesson after this is made. I'll teach you how to use the Vernier caliper, and we'll talk a little bit more about design rules. Now next week what we're going to do is we're going to really get into more advanced design rules, but today I wanted to introduce the concept and show you how to use the Vernier calipers. And then as we move forward, we want to start sharpening our design skills. Now, some of the design skills that I want you to use are, number one, to always design to design rules. And then after we get that work done, what I want to teach you is how to always design using parametric design principles. So far, we've not been using parametric design principles because I want you to have a little fun with the design. I want you to have a little fun with your printer. And if I just teach you theory and teach you good practices, you're going to get bored before you get to do anything exciting on the printer. So I'm trying to kind of build all of these things together. But let's go ahead and I'll pause the video and I'll catch up with you guys in just a minute. And we're back, and you can see that our print has successfully finished. Very nice. And when I look at these, it's a very, very beautiful print. Do you see how our embossing just worked absolutely perfectly? Very smooth, not a lot of trash in there. And then on the square cube, we can see this was the plane that is perpendicular to the x-axis. And then this is the perpendicular to the Y, and this is perpendicular to the Z. And so these structures are the structures that we're going to use to initially begin to get an idea of what the precision of our printer is. We're trying to define a set of design rules for our printer, and we need to first understand how precisely we can print. If we say we want something 25 millimeters, does it come out 25 millimeters? Does it come out 28 millimeters? Does it come out 26 millimeters? And that way we can design and develop tolerances based on the manufacturing capabilities that we are using, if that makes sense. I hope it does. So I need you to get out your trusty set of calipers. I hope you all have your calipers now. If you don't, look down in the description. There is a link where you can get the exact same set that I am using on Amazon. And guys, as I've been using this set of calipers, they're really, really nice ones. And let me kind of show you. You open it up, And the first nice thing that you see that it comes with a battery, so you don't have to go out and you don't have to hunt around trying to find this little battery. And the other really nice thing is it gives you this freakishly small screwdriver to take the battery cover off to put the battery in. If you're like me, you got your calipers, you saw the battery, thought I better put it in, and you took the thing apart to put the battery in, only to find that this is not the battery, this is the spare battery. There should already be a battery in here. And let me go ahead and get these out, and this is what we need to do. This is what we need to use in order to be able to begin to understand our design rules. It is a vernier caliper. It will measure three things very, very conveniently. It can measure outside diameters, it can measure inside diameters, and it can measure depth. And let me show you how these things work. Let's see, let me get my prints out of the way here. Let me pull this on out and get it where you can see it. The first thing is you need to turn it on, and you turn it on obviously with the on-off switch. You can see that it comes to life. And then what we should expect when the system is completely closed, that is, this unit is pushed all the way to the left. When you're holding it like this, it should read 0. You can see that this is reading 1/100th of a millimeter, which is just minusculely small. But what you need to always do when you're starting using these calipers, you need to tear them or zero them. And the way you do that is you get this roller knob, and this roller knob is what allows you to set position. And it's got kind of a slip fit to it, so you press the roller knob against the little metal ruler gauge and you roll it, and then you can see it start spinning. But the reason for that is that you're always applying a constant torque to this, because you see, if I come over here and it's reading minus 0.002, if I push it really hard, I can move it around. Why? Because if you push it really hard, you can actually flex it a little bit. Even though it's stainless steel, it'll bend a little bit and it will affect your readings. So to get accurate readings, you always want to apply a constant torque to it. And you do it with this little roller thumb knob here. Okay, so that is how that works. You can see that I rolled it up against this. Now I need to zero it. When I hit 0, it takes that position and it calls it 0. Now, what I should also say is you always use this, because not only if you press real hard can you torque this and it affect your reading. For something like a plastic part, you can press it so hard you compress your device under measurement. You can compress your device under measurement, and that can affect the readings that you are getting as well. And so this is a very handy little feature to allow you to get very consistent and very accurate and very high precision measurements. And guys, this is a precision tool, so treat it like one, take care of it, put it back in the box. Don't use it to knock your prints off your build plate or anything like that. It's a very precision instrument. Take care of it. And so now I said that it could do three things. And what do we mean by outside diameter? This is a cylinder. The outside diameter is the diameter on the outside as from here to here. What is the inside diameter? That's the diameter inside the device that you're testing. And then the depth would be like, you could take a depth measurement from here down to here, or you could take a depth measurement from here to the inside bottom plate down there. So that's the three different things that you can measure. Well, this tool has three different features. A vernier caliper has three different features for measuring those critical dimensions. To measure outside diameter, you just spin this out and you put your device under measurement in here, and then you come down on it. And then when you come down on it, you just use the little thumb screw until it has it snugly, and then you make your reading right off of here. Well, how do you do your inside diameter? Your inside diameter is done with these two claws out here. and they will precisely, when you put this inside and then spread it apart until you contact the two edges of the cylinder that you're measuring, then when it comes into contact, then you're able to make your inside diameter measurement. And then finally, you will notice that this is coming out and in as you move this. This gauge is used to measure depth. And so you would put the device like this inside, and then you would come down until this edge hits the top lip of what you're trying to test, and then you would make your measurement. So you can see it's a very ingenious device for measuring outside diameter, inside diameter, and depth. Okay, a couple of words about good measurement habits. I've mentioned already that you do not want to press down too hard, because you can compress the part that you're trying to measure, and that will affect the precision of your measurement. And the other thing is, you've got to make sure that you have your calipers contacting your device under measurement in a very perpendicular and parallel way. And what that means is that I'll kind of exaggerate it here. You wouldn't want to make the measurement where the thing was sitting in there cockeyed. Now that one is kind of obvious, but one that's not so obvious, if you're not careful and you did a measurement that was askew like this, you're going to measure what? Too long. And so you want the two faces of your measurement instrument exactly perpendicular and parallel to the faces that you're measuring. So make sure that you're not cocked this way a little bit or cocked that way a little bit. Now I am greatly exaggerating it, but you've got to just kind of bring these things in nice and slow and just kind of grab it. And that way you can make sure that you're not getting it off at an angle. And so let's try this. I'm going to come in here and I'm going to start, let's go ahead and start by measuring the precision of this device in the x-axis. We designed it to be what? We designed it to be 25 millimeters. So let's start by zeroing our device. So I come in here. Okay, and then you can see I'm 1/100 of a millimeter off. Just to be precise, I will zero it. Now I'm going to measure from the X face to the X face, so I will open it up, and then I will come in here, and then I will just kind of squeeze down on it. And then what am I measuring? 25.07. And so that we could say is like 1/10 of a millimeter, and 1/10 of a millimeter after out of 25 millimeters is a fraction of a percent. So this, we're getting precision of better than 1% in our parts. Also, what we can do is we can take measurements at different places. And so if I come up here towards the top, you can see that I'm getting 25.04. That's virtually the same thing. You can't really quibble over a few hundredths of a millimeter. And then down here, if I come way to the bottom, I'm getting a little bit like I've got right there at that bottom level. And right there at that very bottom level, you can see that I am reading a little bit higher, 25.12. And we actually saw that when we were making those gears and hubs. We saw that that first layer seemed to kind of smear out a little bit and fill the hole, and the hole not be quite as big as what we had wanted it on the first layer. If we come up to the top, it seems like that we are getting a much cleaner precision of 25.06. And so what I am interpreting is this part that was the first layer that went down to the build plate smeared out a little bit, and that layer is a little bit wider than what the rest of it is. I'm trying to come in above that, and when I come in above that, I get 25.06. It's only when I measure including that very bottom layer that I'm getting the 25.13. So you see, we're starting to learn quantitatively how our printer works. And so I would say overall in the X direction, I'm getting a precision of better than 1/10 of a millimeter, like 0.05 millimeters. If I just kind of go up and down and measure it, I'm getting like 0.05 millimeters along the x-axis. That is really, really good. Okay, that is really, really good. So let's check the y. And so this time we're going to be testing to the y face, because just because you're right in along the x-axis, remember that is the x motor, the x mount, and the x gantry. You have a totally independent system in y, and it might or might not be as accurate as in x. And so when I come in here and I measure this, I'm getting about 0.09. Okay, about 0.09. Let me come down here. I'm getting 0.11. And then if I go all the way to the top and do it, I'm getting a little better. It seems like that top level is best. What I do notice is in this corner, I have a little bit of a ridge on the corner. And so as we are printing this thing like this, when we're printing this thing like this with the X and the Y, there is one corner that has a little bit of a lip on it. That lip is right there. I don't have that lip on this side. It is very, very good on this side. So if I come in and measure, if I come in and measure that, I'm getting a little bit, that one actually looks pretty good. Am I measuring Y? Yeah, I'm measuring Y. Okay, I'm getting a little bit higher, about twice the imperfection that I got along the x-axis. Now I'm going to see if my ridge theory is correct. You can see the ridge is here. What can I do? I can come in and I can bite it like this without going over that ridge. I can come in and bite it without going over that ridge, and look at that. Just like the x-axis, the y-axis is around 0.05 millimeters in precision. So the problem is not the precision of the x and y stage. It just seems the way this was sliced, and maybe where the seam is, I'm getting kind of a seam here on the corner. Because you have to think, when you're printing one object, you hop over to the other object and you have to start somewhere. Usually you can get that tiny little imperfection at the point where you're starting your printing when you're going to the new object. It takes it just a little tiny few millimeters to get right exactly on track. It's probably got a little bit of a glob of the PLA on the nozzle, and maybe that glob layer after layer is leading to that little seam. Is it bad that it's there? No, but we just sort of need to know where it is, so we make note that in the when we're measuring the Y face, it comes out on the back side there. And so that I've got a little bit of a ledge there, and I'm not getting a perfect reading. Now the Z should be interesting because X and Y is going back and forth. X and Y is going back and forth, but Z is going up and down. And so the Z axis is really, really very, very different. And so let's measure the Z and see, like I'm thinking, do you think the Z is going to be a little bit too big, or do you think that the Z is going to be a little bit too level, a little bit too little? I think it's going to be a little bit too little, and the reason I think it's going to be a little bit too little is I tend to put my first layer down pretty low. Like I like to have that nozzle pretty close to the build plate, because I think for me that helps it make the first layer stick. And it could be that that first layer was just a little bit too thin. So let's come in and check and see my theory here. And you guys see what you guys get. Okay, but yeah, you see I'm getting 24.96. So again, a precision of about 0.05, okay, about 0.05 millimeters in precision, and it is it's a little bit short along the Z-axis, and it's a little bit wide along the X and Y axes. So as I do this, what am I concluding about my printer? My first design rule is, when I print something, Do not expect to get better precision than 0.05. Don't expect to get better precision than don't expect to get better precision than 0.05 millimeters. But that is amazing to me. If you look at how small a millimeter is, to be getting it within 0.05 millimeters, that is really, really good. And it's pretty much about the same in X and Y and Z. It's just X and Y, you get a little bit bigger than you expected, and in Z, you get a little bit less than you expected. So hopefully you can see the precision of this tool and the power of this technique, but also just remember the technique that I showed you. The technique that I showed you, that you don't have to have it completely enclosed. You can come in and you can just sort of grab only partial, and you can still get an accurate reading, and that way you can kind of take out the effect of that little edge imperfection if you want to. Okay, so we did that. I think also what I could do is I could measure that. You see, this edge might be imperfect, this one, and this one, but this one was drawn, and so this is probably going to be the most perfect one. So if I measure from the top, I'm going to take that out. I'm going to take that out and look at that. I've got 25.02. And so that's an even higher precision if we ignore the little lack of perfection along the one corner, or along probably some degree of imperfection on all of those corners. And so you can see that that is absolutely amazing. So what do I take away from what we have just done? I learned how to zero my calipers, and I learned how to use these jaws out here to measure outside diameter. Okay, now this is a circle, as you can see, circular and then cylindrical as opposed to a square, but it works very, very similarly. Now we designed this to be 50, I believe. So we're going to come out here, and here you can see there's always going to be an imperfection where you start and end your drawing layer, and you can see that is here. So I'm going to start by not measuring that. I'm not going to have that seam in my measurement, just to kind of see what the raw accuracy is. Also, don't measure over your emboss, because that is a little flat spot, right? You kind of flatten it out right there. So you don't want to measure over that, because if you did, your measurement would be inaccurate slightly. It would be slightly inaccurate by being a little bit too small. So I come in here. Let's make sure that we're still zeroed. Okay. Always I like to zero. And then I'm making note of where the seam is. And then I'm going to come in and I am going to measure it like that. And I'm getting 49.9. So for these larger objects in a cylindrical object, I'm getting an error of about 1/10 of a millimeter, about 1/10 of a millimeter. Let's see there. Well, that's actually a little more than that, maybe 3/10 of a millimeter. Okay, and let's try it again. About 3/10 of a millimeter. I come down here. 2/10 of a millimeter. All right, now I'm going to measure and see if there's a difference, because this looks circular, but is it really round or is it oval? The way we could see if it was oval, we're going to come here and get it in there, and I'm going to measure 49.78, and so we would say that that's accurate to 0.2 millimeters about. Okay, now I'll come along the x-axis. And along the x-axis, okay, 49.7. So again, about 0.3 millimeters, 0.3 millimeter precision in Y, or that was Y. And then in X, I'm about 0.3 millimeters in precision in X. And that is interesting that it's so much more accurate on a square piece than a round piece. Let me see. I just want to really verify that. Okay, so here I get it. Yeah, that is 0.05. And so we're much more accurate printing a square piece than a round piece. Now you could kind of think about that and see if you could figure out the nature of a 3D printer, why why it is printing a square object more accurately than a round object. But even if we don't exactly know the reason, we know that we've got 0.3 precision in the cylinder and we have 0.05 precision in the cube. Okay, so that is very, very good. Now, different ways, like we want to measure the inside diameter. What's one way that I could measure the inside diameter? I could take the outside diameter, 49.76, and then I could come in and I could measure this. Okay, and so I would subtract 5. Wow, that is really accurate on that wall thickness. That is a few hundredths of a millimeter. So I would subtract 5, and then I would come over here and I would subtract 5. Okay, so I had about 50. Okay, I had right at 50, and then I would subtract 10, and the distance between here and here is 40. Well, how could I directly measure that? Well, I could come in here like this and I could line it up and eyeball it. No. I used to see people using calipers and they would do that. They would be sitting here trying to do this and eyeball it to measure the inside diameter. No, these claws are your friend. Now notice when you close it, this edge and this edge are face to face when you close it. So what I can do is I can come and I can put those on the inside. I can put those on the inside. And inside is a little harder to measure. Okay, inside's a little harder to measure. You really want to make sure that you're right on. And then I am at 30.97, but I might be cocked in there a little bit. So let me make sure that I've got that just in there, just right. And yeah, it looks like that I'm about 0.25 precision, about 0.25 precision in that direction. Now be careful about just grabbing it by a little bit and really going too hard with it, because you could kind of dig into the plastic and affect your measurement. But what it looks like is about 0.3 of a millimeter in precision on this round object, and on this nice simple square object I'm getting precision of about 0.05 millimeters if I ignore the little imperfections at the corner. Does this make sense, guys? Okay, now how tall is it? We would expect this to be a little bit small as well, and I think we extruded it to 30. And so let's come out here and look, and that's coming in at 29.83. Again, it's not quite as tall as we designed it, and it's off by about the same amount that the square was. And so we come in a little bit thin in the Z direction, but that is still, let's say, 0.2. And then let's see how far off we were on this one in the Z direction, in the height direction. And trying to get, yeah, that one's about 0.05 as well. And so we're off by 0.05 in, that one's a little bit more, that's like 0.2. So this one has more uncertainty, like 0.2, to where this one was much better than that. Okay, but that is still really good and very close to what we wanted. Okay, now how do we measure the depth of the hole? Well, there's three ways we could do it. One way we could do it would be to come in, and I could use this depth gauge, and you want to get it where it is longer than what you're trying to measure. Can you see how that's longer than what I'm trying to measure there? And then what I'm going to do is, that's very confusing when these things start coming into my other camera view, so I'll try to stop that. So now I set this down on something firm, and you want it to be something flat and square, and now you hold this part of it, okay, this part of it, and you just bring it down, and that is showing 29.87, so say 29.9, what we were getting the other way, okay? Now, if I wanted to know how deep the hole was, that is pretty easy. What I can do is I can come up here, and then I can stick it inside, and then I can bring it down, and then when I bring it down, I'm measuring a depth of 20, and that is just like within 1/100 of a millimeter of what it was designed for. It was within 1/100 of a millimeter of what it was designed for. So usually you can just come in, and the most straightforward thing is to just go like that, and I didn't do that one very well. I need to be more careful. Okay, 20.002. So that depth is just very, very precise. Why do I think the depth from here to here is more accurate than the depth from here to here? Because this one has the uncertainty of what's really happening with that first layer that you put down on the build plate, and this one was made in the middle of the build, and everything has kind of worked its way out at that point. And so I think that distance between a bottom and the top is going to be more accurate, which we're observing, than the difference between the top and the absolute bottom, if that makes sense. Now, usually what I just showed you will work, but I want to show you another way. And what I want to show you is if you don't want to do the math, you can come out here, get it longer, and I can come here, okay, like that. And now that says 29.92. I can zero it there. And now this is my 0 point, and any measurement I make is relative to this. So now I will come in, and I will put it inside and come down, and then what do I measure? That? Yeah. Okay, that would be then the thickness of the bottom, and the thickness of the bottom is 10, because it took from here to here is the 0 point, and then it measured down to there, and then it told me what was left. And so you guys can think of different clever ways that you can zero this thing that then will allow you to directly measure the part that you can't get access to. Okay, so imagine if for some reason I couldn't do it in a convenient way like I showed you. Always think about choosing a reference point and then zeroing to that reference point, and then measuring a different point, and then that will oftentimes give you access to that dimension that you're having trouble getting to. Now, what is absolutely true is you can always just jot it down and do the math, and if it's 30 and 20, it's really easy to do the math, but sometimes if you're just clever with your zeroing, it will make a big difference. Okay, so let's think about what we are learning here. If we are making square, simply shaped square objects, our precision is absolutely incredible. You know, a few hundredths of a millimeter. We've learned that there's going to be imperfections on our corners as we're going up, and those little tiny imperfections can affect our overall precision of our component. On this, if you were really going in a precise application, you could just kind of sand that little imperfection off if you wanted to. What we've learned is on round objects, the precision is not quite as much. Maybe it's just the complexity of the shape, or maybe it's not as accurate with curves, but still within, still a 1/10 of a millimeter or better. It seems like everything that I've done today has been within a 1/10 of a millimeter or better. So, that was not good. Okay, so you see the things that we're measuring are all within a 1/10 of a millimeter or better. And depending on how you set your nozzle height as you were leveling the bed, you could find, it is possible that you could find that your z-axis dimension is a little bit, off. I think I made that last measurement with the without being zeroed in the right spot. But you see, we're a little bit short. We're a little bit short in the z-axis on all of our components. Okay, did it make sense how to use these these Vernier calipers, and do you see the power that comes from being able to understand how closely you can manufacture something to how you designed it? Because it's not about getting, 30 millimeters on Fusion 360. It's about getting 30 millimeters in what you designed. In your design rules, you never want to try to achieve a greater precision than what you can manufacture. And you can design things a lot more accurately in Fusion 360 than you can manufacture them. Now, every manufacturing technology is going to have different tolerances. If you're using machine tools, a lathe, a milling machine, a CNC machine, you're going to have a completely different set of tolerances and a completely different set of design rules. But you want to understand the design rules before you start designing things. So let me think of what are some other things, okay? What are some other things that would be design rules that we need to understand? Okay, imagine you have a block and you have a slot in the block and you have another slot in the block. How closely can you bring those slots together before the wall isn't there? So it's sort of like, how tiny of a wall can you build for a slot? And that will be a design rule. How closely can you design slots together? Another one would be if you have a wall. You could make a wall this big very easily, but how narrow can you make a wall before the wall isn't there? Another one would be, so one is the wall of the slot, like how closely you can bring slots together before two slots become one slot. Also, let's just say that we had one slot. How narrow can you make a slot until there's no slot there? Okay, so if you tried to make a slot at 0.05 millimeters and then you printed it, would the slot be there? You see, those are things that you need to know before you jump in and start designing. Even though so far in this class we've kind of just jumped in and started designing. And the reason I've done that is, and I get some complaints from people of something that I'm doing that's not exactly the right way or proper way or best way to do it. You see, I want to keep you interested in this class, so I tried to get out there and get some really fun stuff going. And now we're going to come back and start cleaning up our design habits, because I felt like if I spent 10 lessons on measurements and design rules and precisions and tolerances, you would lose interest in the class. So we're going to move forward improving our design skills and our design techniques, and we're going to improve our knowledge of Fusion 360. We're going to improve our print skills, and we're going to improve the precision of the printer we have. We're going to be upgrading and tweaking the printer as we go along. Several of you guys have been asking if I would go ahead and give you a list of the upgrades that I'm doing. You see, the thing is, I ordered off Amazon almost every possible upgrade for this printer, intending to figure out the ones that work the best and the ones that would be the best value for you, and then start you upgrading your printer with the lowest cost upgrades that give you the maximum benefit. And so if you look at something like the extruder assembly, or the little geared mechanism that drives the filament, I ordered like 4 different versions of upgrades for that. And what I'm going to do is I'm going to see which one works the best. I ordered a bunch of springs to get better alignment of the build plate. Which spring set and knob set seems to be the best made and works the best. And so I've ordered multiple versions of different upgrades, and then when I see what's best, then I will bring you along. So I don't want to just give you a list, because I don't want you to have to order, I ordered a bunch of junk, so you won't have to. Okay, I hope that makes sense, but we'll be doing the upgrades as well. I think the other thing, as far as design rules, we would like to know, I said, how small of a slot can you make? How small of a wall can you make? How close can you bring 2 slots together? How narrow of a wall can you make? And then how narrow of like if you make two walls, how closely can you bring those two walls together before you leave the gap between the wall. And what's happening up here with walls and gaps is different than what's happening down here. So bringing slots together is different than bringing walls together. And so we're going to want to understand those design rules. Also, we want to understand our tolerances for something like if you think of that gear on the hub, okay, like what tolerance should we have where it's snug but moves very easily? I think we've been kind of guessing at 0.2 millimeters. Well, what we're going to do is we don't want to guess. We want to have a design rule for that. So anytime we have sliding surfaces, how much tolerance should we have? Okay, that's pretty important. I think also if I had a post and and then I wanted something up here, this up here part is going to have to what? Print over air. It's going to have to bridge between these two things. Now, if they were very, very close together, it's just going to jump right over, right? Okay, but the further apart we get, the harder it's going to be to build that bridge. And so we want to build some bridge structures to understand how our printer is going to work if we end up where we have to have some areas that we're printing over air. That'll tell us, can we just print it, or do we need to build some support under there? Also, you can imagine if I was building something almost vertical, each layer is coming out over air a little bit, but something like that would be pretty easy. But could you build something like this? Probably not. So where between here and here are you not able to get a smooth re-entrant wall? You see, I'm talking about the bottom side. Like this, you know, you're going to be printing over air. It's not going to work. Like this, it's going to work perfectly, but somewhere between those two, you get acceptable results. And believe me, if you want to take your design skills to the next level, you really want to understand the manufacturing when you go in and do the design, and then you will begin with design rules to talk about a new concept I'm going to talk about: design for printability. Design for printability. Because if you design for printability, you're going to get much, much better results than if you just design for animation and to show people the cool little thing spinning around or whatever. And most people design that way, design for animation. But the truly great designers design for manufacturing, and for us that's going to be design for printability. Well, I've talked a lot. I hope I haven't driven you guys crazy. You all were probably ready to sign off when you saw the river scene back there, but this is important stuff. We're going to spend a few lessons on it, and then I think that I'm going to come back. The other thing we need to clean up is we've been designing like a bunch of cowboys, and what we want to do is we want to come in and we want to learn how to design using parameters, to do parametric design. You guys that took the earlier Fusion 360 lessons will remember that, or you guys that took the Visual Python class, you'll remember it. But we're going to go over design for manufacturability, and so that will be parametric design and design for manufacturability. So those will be two really important things coming up, and I want to continue to teach you Fusion 360 in the concept in the context of a project. And so instead of just going in and showing you these are all the ways that you can join things together or assemble things, I want to have it in terms of a project like a gearbox, and then I'm going to show you how to do assembly based on the design that we're doing. And it was just hard. I went back and forth between those two, but I just think if I show you a list of menu commands on Fusion 360, when you really need them, you're not going to remember them. But if we learn them one by one as we're doing neat and cool projects, I think you'll remember. I hope you guys are having fun. I'm seeing some really impressive work that you're doing in the homework assignments that you posted, and so really love it when you post your homework. If you guys like this video, give it a thumbs up. If you've not already, subscribe to the channel. Leave a comment down below. That helps me with YouTube showing more potential viewers this video, and then share it with other people. You know, if YouTube isn't showing us a lot of love these days, just find someone that you can get into the hobby. It's a really, really rewarding hobby to get into. And you know that's important because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.